So welcome to this session. In this session, I'm going to start with showing you an 8085 simulator. So before we do any more programs, I'm going to show you using a PC-based simulator. We can emulate the programs of an 8085 microprocessor. So this program, 8085 simulator, the link to download this simulation software, I'll provide that to you in the Google Classroom, as well as you can actually download uh, from your Play Store onto your Android device an app. Fine. So there are a number of 8085 simulators available online, both for the PC as well as for Android versions, Android mobiles, and probably for iOS devices as well. Uh, but the one that I'm going to show you, this 8085 simulator, it's much better because it gives us the real feel about the 8085 microprocessor, the keyboard layout of the actual microprocessor, 8085 microprocessor, and this 8085 simulator that you can see on your screen is almost similar. You'll see the same buttons, this reset button, previous, next. They might be having the names decrement, increment. Here it's previous and next. Go, execute, examine memory. So this examine memory, examine register. So these will be the uh, uh, these buttons are also available on your 8085 microprocessor, and you also have 0 to F hexadecimal uh, numbers that you can actually enter into your microprocessor. So instead of using any other 8085 simulator that's actually available, I'm using this one because it gives us the actual feel of the real 8085 simulator. This keyboard layout is similar to one we have actually in the lab. Uh, so what you can see here is so how to enter any program in this 8085 microprocessor. So we have done a number of programs so far. This is the very first program that we did, had 4F to 78. So keep note of the memory, the address locations, and keep note of the hex codes. So what we'll be doing is we'll be entering the starting address, fine, and then we'll be entering the hex codes. We have to enter only the starting address. Rest of the addresses will be incremented on their own. The program counter will after that increment the PC, the program counter on its own. We'll only be entering the starting address into the program counter. After that, every machine cycle will increment the program counter on it of its own. We'll only be then entering the hex codes into these memory locations. Uh, Fine. Yes. So this is the first program that we have done, and I'll be simulating this program using. So instead of adding 4F to 78, what I'm going to do is I will be adding 01 to 02 so that we know the answer to 01 to 02 is 03, right? And secondly, one more thing you need to note in this case is that this 8085 simulator allows us to only access the memory locations from 8000 to FFFF. So since we had entered these hex codes starting from memory location 2000, but the simulator here, it allows us only to access memory locations from 8000 to FFFF. All the other memory location from 0 to up to 8000, they are actually uh, stored 0 to 7 FFF. Actually they are used by this microprocessor for uh, executing some other programs. So we can actually see if I try to examine the memory location 1000, and I'll click. So it will give me this error. So it will show this error actually reads that 0000 to 7FFF. The H represents the hex code, hexadecimal number. So it is reserved for internal memory for processing by the ROM, and for the user only 8000 to FFFF is available. Fine. So you will get this error code. Maybe you are not able to see this right now, but you will once you execute this, once you try to access the memory locations, you will receive this error code. And so the accessible memory for us is 8000 to FFFF. So instead of starting the program from 2000, I'll start the program from 8000 up to 8006. So I have to enter the program from 8000 to 8006 instead of 2000 to 2006. That's the only change I'm going to make right now. Right? So now how to enter this program in the microprocessor. Fine. So first you have to click on this option, examine memory. And which memory I'm going to examine? I'm going to examine the memory location 8000. After that I'll click next, and what I have to enter at this location is the hex code of this instruction, that was MVIB 4F, that is 06 is the hex code for this instruction. So I'm going to type 06 here. Fine. So once I enter 06, then I'll click next. Now automatically the microprocessor will move me to the next memory location, that's 8001. There I have to enter the data byte. So we had entered the data byte 4F. Instead of 4F, I said to you, let us add 01 to 02. So I'll enter 01 here. Then I'll click again next. And I am typing MVIA not 78. I'm going to enter 02 in the accumulator. But the opcode for MVIA is 3E. That remains same. 3E. Fine. Next. At the next memory location, I have to enter the next data byte. So let it be 04. Fine. So I have entered. I have two registers. One is B. In that I have entered the operand that I have entered in the B register is 01, and the operand that I have entered in the accumulator is 04. So the resultant should actually be 05. So we have reached to this memory location where we have to enter the opcode for add B. For add B, the opcode is 80. So I'm going to enter 80 here. Clicking on next. Then I have to store that whatever was in the accumulator, I have to store that to memory. I have to store that in the register B. Opcode, the instruction for doing that is move B comma A, and the opcode for this is 47. Type 47 at this memory location. Next, at 8006, finally you have to enter the halt instruction, the opcode of which is 76. 76 represents the halt instruction. Fine. So this is actually done. So whatever is in 80000 to 80006 has been now stored in the microprocessor. Even if I reset this, again I jump to examine memory 8000 and click next. It will automatically show that at this memory location 06 is stored. I can click on next, next. You can see 8000 to 8006. These locations have now been set with these data bytes, and unless I flash the memory, this is going to remain in these memory locations, or I have to simply turn off this simulator and restart it to flash the memory of this simulator, not the processor. Now to run this program, what I'm going to do is click on go, then type the memory location from where you want to start the execution of the program, that is 8000, and then click on execute. So it will on your right hand side you can actually see from 8000 to 8006 we had entered these opcodes. So we were at 01 we have entered at 8001 we have entered 01, and 8003 we have entered 04. We are adding these two operands, and it also actually shows you how many bytes each instruction consumes. At this here you can see the registers on your left hand side, left bottom of your screen. The registers are given to you. In A, the accumulator basically will store the addition, that is 01 plus 04. We actually also transfer that to 05 to register B. So you can see both A and B, they are carrying the resultant, that is 05. We had no dealing with C, D, E, H, L. The program counter is actually pointing to 8007 because already up to 8006 the programming has been done. The program counter now will be already pointing to the next memory location where the next instruction can be or may be. Fine, so that is 8007 in this case. So you can see also the status of the flags. Sign flag is obviously 0 because this is a we are actually have a positive number here. Z is 0, auxiliary carry is 0, parity is 1, that means it actually represents an even number. So if you can see 05 is actually 11101, right? So if you talk about 8 bits of digital numbers, it will be actually 00000101. So there are 2 ones in this digital number, and therefore the parity is even, therefore parity has been set to 1. So this was your first program that we had performed using that I have actually shown to you. Let us see another program. So let's take the example of this program that we that have shown to you earlier. Write a program to exchange the data at 2 different memory locations, 5000 and 6000. Since 5000 and 6000 these memory locations are not accessible to me in the simulator, so instead of having 5000 and 6000, let us say we have 2 memory locations, A and B. We have data at these 2 locations. We want to exchange the data at these 2 locations. So fine. So let's go to the simulator. So first of all, reset. So what we want to do right now is examine memory location A. Let us first of all store the data at these 2 memory locations, that's A and and B. Fine. So A at this memory location, simply examine this memory location, type any data. Let us say at this location the data is 15. Fine. So this is stored at this memory location. Similarly, you can examine the memory location B, and at this memory location, let us say I am entering the data B6. Fine. Next. So this is now stored in at these 2 memory locations. So you can actually go to these 2 memory locations. You can examine A. Click on next. So it will show you that at this memory location the data is 15, and similarly examine B. Click on next. You will see the data at this memory location is B6. So these two uh, So the data at these two memory locations have been fed, and we want to now uh, enter the program. So what you'll do is we can enter this program at any memory location. Let us enter this program at memory location 9000. Next, so in the original uh, program, uh, we had entered this program at address 2000, but since as I've been telling you that 0000 to 8000, actually 7 FFF is inaccessible to me. So from 8000 to FFF, that is accessible to me. So I am using any address after 8000. So right now let us assume we are entering it from 9000, so it will go up to 900E. Fine. So these are the op codes, the hex codes that I will be entering. So I have 3A. 3A is the op code for LDA instruction. So at 3A, I am entering, at 9000, I am entering 3A. Click on next. At 9001, I have to enter the least significant bit of the memory location. Now remember, instead of 5000 and 6000, the two memory locations where I have stored data is A, B, 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 B. So instead of 5000 here, I have A. So I will be entering first the least significant bit. Least significant bit is also A, and then the most significant bit, that is also A. So this completes my first address location, that is A. Fine. Instead of 5000, I am having now A. Click on next. Now what we have to do after this is move B comma A. So whatever was now the contents at A, we have loaded that at the in the accumulator. But from accumulator, we want to first of all move it to memory, to the register B. For that, we have to enter the opcode 47 at this memory location. Click on next. At 9004, I have to now enter LDA. Instead of 6000, I have BB. Fine. The opcode for LDA is 3A. That means same. 3A. Click on next. Now I have to enter the least significant bit and the most significant bit of the second memory location, that is BB. Click on next. BB. Click on next. So now we are at 9007. That was actually 2007 originally. At this point, now whatever is in the accumulator, that's actually the contents of 6000. I will be transferring that to 5000 by using the instruction STA A. Instead of 5000, I have A. So first of all, the opcode for STA is 32. So enter 32 at this memory location. Click on next. Then enter the least significant bit of your address. Next, and the most significant bit. Next. Now we are at 9008. That was originally 200A. So whatever was now in B, transfer it back to A. For that, I have the opcode 78. Fine. After this, use again the STA instruction. STA BB. For STA BB, you have the opcode 32. And then next, you have to enter BB. Then click on next. BB. Click on next. Fine. We are reached the end of our instruction. Type then halt instruction. So if you will not be typing the halt instruction while execution, you will run into a loop. Not a loop, but you will, since there will be no halt instruction, the microprocessor will not understand where to stop. It will keep on executing even if the data byte at every memory location of that is 00, but it will keep on decoding 00 for infinitely after it reaches FFFF. Fine. So we have now entered the data. We have entered the instruction from 9000 to 900E, and we have the data at A and BB. I have not executed the program yet. Right? So let me reset it. Let's go back to the memory location A. Next, just for again, what we have at A is 15. Fine. Let's examine memory location B. What do we have at B? We have B6. Fine. Now let us run this instruction. Now what should happen is that at A, B6 should be written, and at B, 15 should be uh, available to us. Fine. Let us reset this. Uh, Go. Where is our program? At 9000. Execute it. So this is your execution. So this actually shows you that your program is running fine here. So it will actually also tell you what you have actually entered and how many bytes of data you have everywhere. Now let us check whether our program has run successfully. Now we will examine the memory location A, 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 A. Before clicking on next, what do we expect? At A, we are now expecting instead of 15, there should be B6 at this memory location. Click on next. You have B6 at this memory location. Fine. Now let's examine B. Instead of B6, what should be at this memory location now? 15 should be available to me at this memory location. Click on next. Fine. So our program is running. We have exchanged the data between two different memory locations, that is A and B. Fine. Originally, when I had actually shown you this program, we had the two memory locations 5000 and 6000. And since they are inaccessible to me, I have used two other different memory locations B. You could have used A000 B000. So it was also you can use any memory location. You can exchange the data between any two memory locations. You can do that easily. So even if you want to change this program right now, say for example, instead of having the data at A, I will only change the least significant bit at 9001. So at 9001, I have AA right now, but instead of that, I will say, for example, enter 00, and I will click next. Right. So rest of the program I have not changed. So what I will do is now, click on go, click on 9000, and click on execute. Right. So instead of 9000, at 9001, you have now, what do you have? You have A00 instead of A. So you can actually debug the program also easily in a microprocessor 8085 by simply changing the opcode or the hex code at any particular memory location. The rest of the memory locations you do not need to change; they will remain as it is. So this program has run smoothly. So at actually, when we actually changed A00, we had to actually change at 9008 also. Uh, examine memory 9008. Here also you have to enter 00. Right? So now I can again execute this program. Fine. So at 9008, I have entered 00. At 9001, I have entered 00. So instead of exchanging between AA and BB, now I'm exchanging between AA00 and BB. Fine. So whatever was at BB, so at BB, uh, I had 15. That would have gone to A00. Since I executed this two more times after that, whatever was at available to me there, that went back to BBBB, then that went back to A00. So you can actually run this program as many times you run this program. So this exchange will keep on happening here. So you have to keep uh, so you have to keep that in mind. So the number of times you execute this program, the exchange will keep on happening. So sometimes you might run the program twice. You will end up at this with the same data byte that was already at that memory location. You will say that this program is not running. No, it is running, but since you have run the program twice, the exchange has taken place twice. That means whatever was earlier in that memory location, that has come back to it after two operations. So you need to keep that thing in mind. uh, Fine. So let us do one program that we had done yesterday and day before yesterday on Wednesday. The video I shared with you. Mm, Let us multiply 3 and 5. Fine. So this is the program that we had done yesterday. I have managed to change these. I have entered the opcodes here, and something that you can also check from the table that I have already provided you. I have also modified the address uh, locations as per the simulator requirements. Fine. So these are the opcodes that I will be entering from 8000 to 800A. So fine. So let's reset this. What Where we have to go? We have to go to memory location 8000. Click on next. So you are actually seeing 06 is here because this is the earlier program that we have done at this memory location. But we'll just overwrite it. There is no issue with this. So at 8000 I have to write 06. Fortunately it remains the same. At the next memory location I have to enter 03. So I'll click 03. Next at 8002 I have to enter 0E. 0E. Next. So this is all these locations. Then I have 05 here. Next. So this is a multiplication program. You are multiplying 03 with 05. And XRAA, for that I have changed opcode AF. Next, add C is 81. Next, then you have 05 C2 05. Next, C2. Next, then you have 0580 76. 05. Next, 80. Next, 76. Next. So this is done. Now I can run this program. So go. It's located at memory location 8000. Execute. So this is done here. Fine. So this shows you your program from that you have written from 8000 to 8009, and it will also show you how many times this loop basically jumps. So this loop will actually jump thrice as we have seen yesterday, and therefore that means this loop is actually running 3 times including the first time, and finally you have the halt instruction. So you can see this program is running thrice, so the output will be actually 15. And where is that output being stored? That is being stored I guess in the memory location it will be stored in the accumulator. So you can see actually the value of the accumulator, that is 0f. So 0f actually represents 15 in decimal number system. So 3 into 5 is 15. So you are getting 0f. You can actually modify these two numbers 03 and 05. Let us say I will enter 02 and 04. So at 8001, so examine memory 808001. Next, uh, at this point there was 03 stored. I will override this and I will say I will let 02 be stored here. Next at 8003 instead of 05 I will store 04 and click on next. So this is done. Now I have to run this program again. So go 8000 and execute. So the program runs again, and you can see, as you can see, this program will actually have now only will only run twice. The loop will only run twice before it hits alt. And 2 into 4 is what? 8. So you can see in the accumulator the number is 8, and it is 8 in case of hexadecimal number system as well as in decimal number system. 2 into 4 will be 8. So this is multiplication program that we had done. Similarly, we have done other programs. We did yesterday find out the maximum between two numbers. So you have to complete this table, find out the X codes of each and every instruction, and see how to execute it. Similarly, then we had done write a program to count the number of ones in a register and store the result in C. What else? So we had done these 3-4 programs yesterday. So enter these programs in the simulator and try to execute them. Also, you can find out more programs. I'll actually be sharing a document with you in which there will be a number of programs. You try and execute each and every program and see how they are running. So we will start with interrupts interfacing in the next session. That's all for this session.